Hello and namaste everyone. Welcome to lecture 47 of this course on stochastic approximation. So in the last 2 weeks we looked at applications of reinforcement learning. We will be continuing this discussion over the next couple of lectures as well. And if you remember, in the previous week we sort of looked at the analysis of tabular Q learning. That is, we wanted to identify the optimal policy, and in wanting to do so, we focused on identifying or estimating the Q value function associated with the optimal policy, which we denoted it as Q star, right. And as we said, Q star lives in this SA dimensional space, right, and in general it will be very large, but suppose we are in settings where this SA dimension is not very large and we can indeed work with these SA dimensional vectors, then we came up with an algorithm which we referred to as the Q learning algorithm to get to estimate this Q star directly, right. And once we estimate this Q star, the greedy policy associated with Q star we showed was optimal, right. And we discussed the convergence of this algorithm and so on and so forth. And in today's class we are going to take this discussion further. In particular, we are going to ask what happens if we try to do Q learning in a large state action setup, in which case we are forced to work with function approximation. And the idea then, or the goal then, would be to ask, would Q learning with a function approximation version still help us or not. So that is the question that we are going to ask in the next couple of lectures, and let us see what is the answer that we get to that. So let us begin our formal discussion. So as I said, last time we looked at tabular Q learning, or the version of Q learning with no function approximation. So whenever I say tabular, I mean it is without function approximation, and the update rule that we looked at had the following form, that is Qn plus 1 is Qn plus alpha n times some delta n times E of Sn an. This E Sn an or E SA in general is a standard basis vector sitting in the R cardinality of S times cardinality of A Euclidean space, and ESA is the vector whose S8th coordinate, that is little s comma little 8th coordinate, is 1 and all other entries are 0. So using that we can define this E Sn an vector, and delta n is a scalar which is known as the TD error, right. And the TD error basically looks at the difference between a new estimate of Q star SA and subtracts it, or looks at the difference between a new estimate of Q star SA and the previous estimate of Q star SA. So the previous estimate of Q star Sn an is this, and this is the new estimate of Q star Sn an, and we look at the difference between the two, and that is why this is referred to as the temporal difference, right, of your Q star estimate, right. And then we use this temporal difference in the following way in the algorithm, and we showed that this algorithm converges to Q star, which is the Q value associated with the optimal policy, right. And we had emphasized that these Sns are chosen from the stationary distribution associated with some behavior policy. The word behavior policy means that we interact with the environment using some policy, right, and that policy could be very different from your optimal policy, right. So the behavior policy is one with which we interact with the environment, and that could be very different, and we are forced to do that because we do not know the optimal policy, right. And this d nu over here is the stationary distribution associated with the behavior policy, or the Markov chain induced by the behavior policy, and this action an is chosen according to your behavior policy, while Sn prime, so I should perhaps not put Sn plus 1 here but Sn prime over here. So Sn prime is chosen or sampled from your transition kernel. Is this okay? And we said that if you do it in this way, and if nu is arbitrary, right, and as long as these quantities are strictly positive and so on and so forth, one can show that this algorithm that we have over here indeed converges to Q star. So the question that we would like to discuss over the next couple of lectures is, can we do Q learning with function approximation? So as I told you, when we are in a setting where the states and action spaces are very large, we are forced to work with function approximation. So the question is, can we somehow use some variant of this algorithm when we are forced to work with function approximation? In particular, in this class and the next couple of lectures, we will focus on the in some sense or relatively easy case of linear function approximation, right, in which we have been given some feature matrix phi. So phi is a matrix of size or the number of nodes equal to the product of the cardinality of the state and action spaces, and the number of columns equals d, and typically we will presume that this value d is sufficiently small as compared to the product SA, right. So instead of searching in the whole of RSA space, what we will do is we will search in the column space of this matrix phi, where the column space is d dimensional, and hence we are restricting our search space to a smaller space, and the hope is that by restricting ourselves to a smaller space we will reduce on the computational effort and time, right, and we are able to find a vector theta star such that phi theta star is approximately equal to q star. So if phi theta star approximates q star very well, then by looking at the greedy policy that is associated with phi theta star, we would have a good estimate of the optimal policy itself, right. So this is the goal. In other words, we want to find an estimate of q star within the column space of phi, and this restricted search is what we will refer to as trying to do q learning with function approximation. Okay. So of course if pi star was known, so recall that q star is the q value associated with the optimal policy which we are denoting by pi star. So if pi star was known, right, 2 weeks back we had discussed the problem of policy evaluation. So if pi star is known, finding q star is equivalent to evaluating the value or the q value in particular of this policy pi star. Is this okay? And in that case, that is when pi star would have been known, we could have used the standard TD0 algorithm to get an estimate of pi star, right. In particular, the TD0 algorithm could have been used to find the fixed point of the projected Bellman operator. So what is the projected Bellman operator? It is the product of this matrix or projection matrix H subscript d pi star, I will tell you what this means, times t pi star, right. So if pi star was known, t pi star is your Bellman operator, right, associated with policy pi star, right, and this H d pi star is the matrix that is given over here, right, and one can see that this H d pi star basically does the job of projection. In other words, if I am given some arbitrary vector q and multiply it with H d pi star, then the output that I will get, right, can be represented as some phi theta q, where theta q is basically the theta vector that minimizes the distance that is mentioned over here, and notice that the distance is influenced by d pi star, where d pi star is the SA cross SA matrix, right, in which on the diagonal entries you see the stationary distribution induced by this pi star policy, and it is multiplied by pi star of A given S. In other words, this d pi star, okay. So the SAth diagonal entry, of d pi star would be d little d pi star of S times pi star A given S, right. So this is different from what we, slightly different from what we had in the TD0 algorithm that we had seen 2 weeks back. There this diagonal matrix was S cross S. However, since we are working with q value functions, okay, these matrices will now be SA cross SA, where S by S I mean the cardinality of the state space and A I mean the cardinality of the action space, right. So as I told you, if we had known pi star, then the TD0 algorithm would have found the projection of I should say that the TD0 algorithm would have found the fixed point of the projected Bellman operator. Is this okay? So this is what we have, we would have got if we had run the TD0 algorithm. However, the challenge is that we do not know pi star, right. If we had known pi star, it would have finding q pi star would have reduced to the problem of policy evaluation. However, we do not know pi star, hence the problem becomes challenging, right. So now the question is, with which policy should we interact with the environment. So one possibility is that we can pick some arbitrary behavior policy nu, like we did in the tabular q learning case, right, and then hope that whatever algorithm that we try to come up with, right, that algorithm manages to find a good enough estimate of q star, right, and such an algorithm has indeed been analyzed in this paper called a unified switching system perspective, right, and ODE analysis of Q learning by Dongwon Lee and Niao He from 2020. So you can look at the details of such an algorithms analysis from this paper, and I would like to highlight that whatever tools that we studied in the previous 2 weeks, those tools can indeed be used to study the algorithm where the states and actions are sampled by using some fixed behavior policy. Is this okay? Which could be very different from pi star. However, if you look at that paper, you would notice that you first of all require some strong conditions under which we guarantee convergence, right, and even if we guarantee convergence, the limit to which the algorithm converges to depends on the choice of your behavior policy, right. So there is no guarantee that such an algorithm, if it converges, right, that limit would actually be correlated with the optimal policy, right. Instead the limit will actually depend on this choice of this behavior policy, and hence the choice of the behavior policy becomes very crucial. So keeping that in mind, we will not be looking at the analysis of the algorithm where the behavior policy is new. Instead we will focus on the case of what is referred to as epsilon greedy exploration, right. On the one hand it is quite challenging to analyze, on the other hand the reason why we want to focus on this is because this is one of the algorithms that is widely used in practice, right. Now the algorithmic details of Q learning with linear function approximation and epsilon greedy exploration is as follows, right. So here is the algorithm associated with Q learning with linear function approximation and epsilon greedy exploration. I am going to give an idealized version of that algorithm, right, that is so that the analysis becomes slightly less challenging, right, but in practice one works with a more sophisticated version of this algorithm whose details I will let you know as we move on. Is this okay? So what is the details of this algorithm? So what we do is we will begin with some theta 0. So theta 0 and in particular phi theta 0 can be viewed as an initial estimate of Q star, okay. So we will somehow start with this, then at the 0th iteration what we will do is we will first pick a policy pi 0 which is greedy with respect to phi theta 0. So by greedy I mean phi theta 0, right, will be a vector of size cardinality SA. So let me just write it. So phi theta 0 will be a vector of size cardinality S times cardinality A. So what we will do is we will presume that pi 0 of at state S, right. So the action that this policy picks at state S is basically argmax over A, okay, of phi transpose SA comma theta, right. So whatever is this S over here, you take that S and you take this inner product for different values of A, right, and maybe I should highlight that this is theta 0. So you take this inner product for different values of A and take that action which maximizes this inner product. If there are multiple actions we will break ties arbitrarily, so we will just pick one action which maximizes this inner product over here, and that is the action that will be taken by this pi 0 policy, right. So in other words this pi 0 policy, that is for n equals 0, this pi 0 will be chosen to be greedy with respect to phi theta 0 where greedy is defined in this way. Then what we will do is we will use this pi 0 to cook up a epsilon greedy version of this policy pi 0. So what does epsilon greedy mean? It is specified over here. With probability 1 minus epsilon we will act according to your policy pi 0, and with probability epsilon we will pick up action uniformly randomly. So this is like a uniformly random policy. So the idea here is that if your phi theta n, right, so if you are in a general iteration n, if phi theta n is a good estimate of Q star, then your pi n will behave like your optimal policy. However, if your phi theta n is a very poor estimate of pi star, then with some probability you are not acting according to pi star, and that sort of allows you to explore a bit more, and the hope is that by doing this epsilon exploration with probability epsilon, which is different from the greedy policy, the hope is that whenever we get stuck at some bad policy, we would be able to escape from that policy. Okay, so that's what this epsilon's role over here is, and because of this choice we refer to this algorithm, we say that this algorithm actually uses epsilon greedy exploration. Okay, so let's just quickly summarize what we have done so far. At iteration 0 we have phi theta 0 and we pick pi 0 which is greedy with respect to phi theta 0, then we construct the epsilon greedy policy associated with pi 0. So in this epsilon greedy policy, with probability epsilon you pick an uniform action, right, and with probability 1 minus epsilon you act according to pi n, right. So what does that mean? What you do is you first pick a state which is sampled from the stationary distribution of the Markov chain induced by pi n epsilon. Okay, so that is the idea. How do we get this? Again, as I told you, if your Markov chain is ergodic, right, and if you allow the Markov chain to evolve for some time starting from some arbitrary state, one can pick the state that appears after a sufficiently large number of iterations, and one can then see that the terminal state can actually be presumed to be sampled from this distribution over here. So you sample Sn in this fashion and An from this pi n epsilon, right. So whatever is your state, you pick the action as per your epsilon greedy policy, and once you have this state and this action, you sample your next state, that is Sn prime, from your transition kernel, right. So in this way you would have Sn, An and Sn prime, and using three quantities you define your update rule in the following fashion. So the update rule over here is given by theta n plus 1 equals theta n plus alpha n times the temporal difference by phi of Sn An. So one can ask, how did we come up with this algorithm? Well, we again go back to our strategy of designing the TD0 algorithm. So if you remember, in the TD0 algorithm also we had an update rule which was very similar to this. So whatever recipe we followed there, if we follow the same recipe, one can see that we will come up with an update rule of the following form, right. And the difference between that update rule and this update rule I will soon talk about, but firstly let me elaborate what delta n over here is. So delta n again is referred to as the temporal difference or the TD error, right, and it is given in the following way. So delta n is r Sn An plus max over A prime phi Sn prime A prime transpose theta n. So this inner product you take for different A primes, and then take the max over A prime over here, and then you subtract it with phi transpose Sn An theta n. So you can think of this quantity over here as approximately or the estimate of q star Sn An at time instance n, and this can be viewed as another estimate of q star Sn An, right. So this is based on so let me just do it carefully here so that there is no confusion. So this should be Sn An. Okay, so this is one estimate of q star Sn An, this is another estimate of q star Sn An, and hence this can be viewed as the temporal difference or the TD error. Is this okay? So this is the way we are going to run our Q learning algorithm. So let me go back and summarize, right. So at any time instance n, we pick a greedy policy that is associated with respect to phi theta n. Using the greedy policy we construct the epsilon greedy policy, then we sample the current state using the stationary distribution of your epsilon greedy policy, pick the action according to the epsilon greedy policy and get the next state, that is Sn prime, from the transition kernel, and then we run our usual TD update algorithm, right. And now one can ask, what is the key difference between the TD0 algorithm for policy evaluation and this Q learning algorithm with linear function approximation that we have stated? The key difference is how do we sample Sn and An, right. So in the Q learning algorithm, this Sn and An, right, especially with epsilon greedy exploration, this Sn was sampled from your stationary distribution associated with this epsilon greedy policy, and An similarly is chosen according to your epsilon greedy policy, right. On the other hand, when we want to do policy evaluation, so first of all notice that in policy evaluation we have been given some policy pi, some fixed policy pi, and our goal is to evaluate that policy. By evaluate I mean we want to know what is the value of q pi, right. So, I mean in the previous case we had focused on estimating v pi, but here we are going to focus on an analogous problem which involves estimating q pi, that is the q value function associated with this policy pi. So, in this case your current state Sn is supposed to be sampled from the stationary distribution that is associated with your behavior policy or the Markov chain induced by your policy pi itself, right. So, the policy with which the policy that we want to evaluate is the behavior policy or the policy with which we will interact with the environment. So, in the policy evaluation case this makes sense because somebody has given us a policy or a strategy and they are asking us how good that strategy is, right. So, that is the policy evaluation problem, and what that means is that we know this policy pi, and since we know this policy pi we can interact with the environment with policy pi itself, and hence this statement makes sense. In other words, Sn is sampled from the stationary distribution associated with your behavior policy pi, and An is sampled again from this policy pi whose value we wish to estimate. Similarly, this A prime that is over here, it will be replaced by An prime and we won't have any max operation. In other words, the TD error in the case of TD0 algorithm would have An prime without the max, right. So, this An prime again is presumed to be sampled from your policy pi itself, which is what we wish to evaluate, right. So, in this case, while the update rule for TD0 algorithm and the Q learning algorithm with a linear function approximation in both cases may look similar, right, the way we interact with the environment or the way we collect the experience trajectory, that differs. In the Q learning case, especially Q learning with epsilon greedy exploration, we collect this experiences or this Sn, An, Sn prime tuples using your evolving behavior policy, right, and that behavior policy is greedy with respect to your with your q star estimate. On the other hand, in the policy evaluation case, the states and actions are sampled according to the behavior policy itself. I should be careful, by the policy with which we whose value we wish to estimate. So, that policy itself will be treated as the behavior policy and we will interact with the environment with that policy itself. So, other than these differences, the update rules may look very similar, but because of these small differences, the purpose and the behavior of the algorithms will significantly differ. So, 2 weeks back we had analyzed the policy evaluation algorithm. Today, while the update rule may look very similar to that, we are analyzing the Q learning algorithm, right. So, in a recent paper of ours, we actually looked at some similar algorithm like this, which is known as Q learning with linear function approximation, and we asked what can we say about the limiting behavior of this algorithm, right. So, those who wish to get additional details about this work, you can look up this paper of ours, right. This is joint work with my colleague Professor Aditya Gopalan from ISC, right. And here what we did was, before we begin the analysis, first let us show you some interesting simulation results that we observed. So, what we did was we looked at a 2 state 2 action MDP, right, and so in this case your cardinality of state space is 2, cardinality of action space is 2, so their product is 4. So, your q pi's and q stars, they live in a 4 dimensional space, right, and what we did was we picked up phi whose number of columns was 2, right. So, in this case we work with a linear function approximation where the column space of phi is 2 dimensional, right, and in this setting what we additionally did was we presumed or we ensured that the column space of phi, right, has q star, right. In other words, we ensure that one of the columns of your phi matrix actually involves q star. Okay, so the linear function approximation class that we are working with actually is perfectly realizable because it involves q star, right. So in other words, if we try to find some good estimate of q star within the column space of phi that we are using over here, right, ideally we would like to go to that q star representation itself, because q star lies in the column space of this phi, right. So what we did was we ran this Q learning algorithm that I described in the previous slide, right, and here are some 3 trajectories that we saw, right. So this black dot over here is basically the point from which all the 3 trajectories start. First let me maybe tell you what is this plot over here. So as I told you, we use a 2-dimensional linear function approximation. So any vector in this space can be represented using 2 coordinates. Okay, so those 2 coordinates are theta 1 and theta 2, right. In other words, phi theta 1 will be the vector in the column space of phi associated with the vector theta 1 theta 2. Is this okay? So theta 1 theta 2 basically characterizes the choice of theta, and this black dot over here specifies theta 0. So this theta 0 or phi times theta 0 is the initial estimate of q star, and this is where we start our q learning with linear function approximation algorithms. And if you zoom in closely, you can see that there are 3 trajectories with 3 colors, one is in blue, one is in green, and one is in red, right, and the star over here corresponds to the theta star value which is associated with the q value of your optimal policy, and you can see that it sits at 1, 0. As I told you, we had set one of the columns of your phi matrix to be q star itself. In particular, the first column of this phi matrix was q star, and hence this 1, 0 value corresponds to the theta star such that phi theta star is q star. Okay. So this is where your theta star lies, this is theta 0, and we ran multiple trajectories, and here are the behaviors of 3 representative trajectories. You can see that for every color there is some faded part and some solid part. The faded part basically corresponds to the initial behavior of the trajectory, and the solid part corresponds to the tail behavior. Is this okay? And one can see that you have lot of these zigzag behavior. This is because there is a noise in your update rules, and the noise will sort of make you jump around, and but eventually as the step size becomes smaller and smaller, okay, your iterate start stabilizing and they will go somewhere, right. And one can see that for the red trajectory it seems to be converging over here, right. The green trajectory seems to be converging over here, and the blue trajectory alone seems to be converging to this star which corresponds to the theta star associated with your optimal q value function, right. Now this behavior is slightly surprising, at least it was very surprising to us, because the initial value, that is theta 0 that we have chosen, is very close to theta star, right. But despite this, you see that the algorithm that is initiated at phi theta 0 actually tries to reach to multiple places. In particular, in some case it tries to settle here, in some on some runs of the algorithm it tries to settle over here, and only on a small subset of the runs it actually managed to find q star, right. So this behavior sort of looked very interesting and also confusing for us, and we decided, okay, we would like to use our understanding of stochastic approximation theory to be able to explain what is happening over here, right. And the figure on the right explains what is the greedy policy at the end. So in particular, this red curve corresponds to this trajectory, the green curve corresponds to this, and your blue curve corresponds to this trajectory. So what we are saying is that if you look at the greedy policy associated with phi theta n, where theta n is coming from this blue trajectory or is along the blue trajectory, and we look at the greedy policy. So one can see that except for some initial few iterations where things jump around, pretty soon, right, the greedy policy is constant, and in the case of the blue trajectory the greedy policy is actually pi star, which is the optimal policy, and this is what one would expect, right. On the other hand, for the green trajectory the greedy policy is constant but it is not pi star, right. So here the greedy policy is very different. So what this means is that if you ran your algorithm and if in your run of your algorithm the behavior was according to this green trajectory, then the optimal policy that you would end up figuring out based on the value of phi theta n could be very different from pi star itself. Now along the red trajectory we observed something very strange, right. So we observed that for along this trajectory the greedy policy that is associated with phi theta n actually keeps jumping, right. In other words, unlike this green and blue trajectory where the greedy policy is constant, in case of red trajectory sometimes the greedy policy was some policy pi 0 and sometimes the greedy policy was pi 1 and it was never settling to either pi 0 or pi 1, right. In other words, if you sort of take some theta over here, then phi theta's greedy policy will be pi 0, and if you allow the algorithm to run for few more iterations and look at the greedy policy associated with, let us say, some phi theta n plus m, that is the value of theta n plus m that is obtained after m iterations following theta n's estimate. So the greedy policy there could be different, and we saw that this greedy policy kept jumping. In other words, we observed some phenomena of policy oscillation, right. Now in this case it's not clear why it is oscillating between the two, and what we also found surprising was that neither of the two policies, that is neither pi 0 or pi 1, these are the two policies between which the greedy policy is oscillating between, neither of these policies is optimal. So if you run your algorithm, that is this Q learning with linear function approximation, right, and if it so happened that the trajectory turned out to be as predicted along this red trajectory, then your greedy policy, recall the greedy policy is to be treated as an estimate of the optimal policy. This estimate of the optimal policy will keep switching between pi 0 and pi 1, and surprisingly neither of pi 0 and pi 1 are the optimal policy, right. So this was some toyish experiment that we did, but even in this toyish experiment we saw some rich display of different asymptotic behaviors that is possible, that is on different runs of the algorithm we saw different asymptotic behaviors, and in certain cases we saw that the greedy policy associated with phi theta n was not stabilizing but it kept oscillating, right, and we wanted to understand, can we give some explanation of why this is happening, right, so that in case we understand why this is happening, maybe we can provide a formal or principle fix to ensure that this does not happen, right. And I would like to emphasize that this oscillation and things like that have been repeatedly studied, and it has also been studied that the behavior of Q learning in the function approximation context shows very diverse and strange behaviors. In particular, I encourage you to look at this paper titled Empirical Design in Reinforcement Learning. In particular, if you look at this figure over here, okay, this corresponds to the performance of a variant of Q learning algorithm. Here in fact they work with DQN, which is basically Q learning by using nonlinear function approximation. In particular they make use of neural network, and hence the D over here stands for deep Q network, and there is a mountain car, there is an environment labeled mountain car, right, and there what they do is they run the Q learning algorithm for sufficiently large number of steps, right, and at the end whatever policy that they obtain, which is the policy that is greedy with respect to your Q value estimate that you obtain, they sort of evaluate the value of that policy, right, and on the x axis you have the range of the performance of that policy, in some sense the average of the averaged Q value estimate associated with the terminal policy that is there on the x axis, and the y axis somehow or in some sense shows the histogram or the density of how many times such policies were identified. So first of all you can see that there is a range of values from minus 500 to minus 300, right, and one can see that if you run this algorithm, it is very likely that your policy may end up with a value of minus 450 with very large probability, and in Q learning the hope is that we can find an estimate of the optimal policy, but here it can be seen that on majority of the runs your Q learning algorithm will end up giving you a suboptimal policy, right, and only on few runs would you end up with a policy which has a very good performance, right. On the other hand, you can see there is a non-trivial probability that your Q learning algorithm, right, will actually end up with a policy that is performing quite worse, right. So this in some sense sets the stage for the next couple of lectures, in which we will try to understand why this phenomena is occurring. In particular, we will also try to understand this phenomena of policy oscillation, why it happens, and also the fact that the Q learning algorithm somehow seems to be getting locked at different places in your search space, which did not happen in the tabular Q learning case. In the tabular Q learning case, we were able to show that the Q learning algorithm will almost always or almost surely converge to Q star, which is the value function associated with the optimal policy. So in the no function approximation case, the Q learning algorithm actually does a very good job in finding the estimate of the optimal Q value function, but surprisingly, when you move this algorithm to the function approximation setting, we end up with situations where there can be multiple limiting behaviors, right, for the Q value estimates, right. They can converge to different places, and on top of that, the greedy policy associated with these Q value estimates could also keep oscillating, right. So over the next couple of lectures, we will try to come up with an explanation for why this is happening, and hopefully you can make use of that and try to build your new improved Q learning algorithm. So until next lecture, thank you, goodbye and namaste.